Welcome to the first session. The first session is on rough paths in action, and Terry is the first speaker.
Okay, thank you very, very much, and thank you all for coming. And it's quite exciting for me to be here too. Put this on. But the journey here this morning was less than auspicious, and started off with the train being delayed by a considerable period, and then finished off by my sitting on my laptop and devastating the screen. But in between all that, I'm rather excited by today because I think it'll give you a chance to see some of the things that are going on. Some of them are quite mature, but some of them are really proof of concept, and I hope you'll take that in the spirit that it's meant to be. But as Jane implied, it's partly about giving you a view of how this mathematics can actually have potential impact and actual impact. Right, data science, I'm sure you will understand, is really, changing our world in many different ways. And it's moving so rapidly that it's hard to believe actually that mathematicians have much that they can say. Not that they don't have things to say, it's just that the volume and the momentum of what's out there is so big. And people are having really good ideas out there, rewriting things we thought we understood, like nonlinear filtering, that it's hard to get into that space. And I think this piece I'm going to tell you about today, I think is making an inroad, but it's not an easy inroad. And it's not actually a clear-cut thing that is ever going to really get there because of the momentum. But I think it has some very clear mathematical principles I'm going to try and explain today, but without becoming too technical, that actually get at why it has a role to play. And there is no doubt that it does. There are really two fundamental mathematical points in this discussion. One is that actually there is a sort of, and this is the one I'm going to explain today, there's a natural invariance that using the rough path theory factors out, and that reduces the dimension of many problems quite dramatically. And because you reduce the dimension, there's still big problems, but because you reduce the dimension, you don't need as much data to do something useful as you would otherwise do. And that turns out to be really quite practical in some of the challenges you'll hear later on. And the other one is more subtle, but maybe the people who are in the workshop will understand it, but I won't have time to talk about it very much. And that is really the fact that looking at a path, what you see, doesn't always help you understand what you feel. And better methods of measuring the data tell you that you're going to do better if you understand higher order terms. That bit's a bit complicated to explain, because it really needs you to understand rough path theory, and to some extent I'm going to avoid that. But so there are two separate sets of reasons why it can be useful. It's not useful everywhere. It's fundamentally useful in what I would call stream data. Stream data for me is like these characters being drawn on this image of a mobile phone by your finger. They're things that come in an order and typically have a complex behavior. In fact, when you really stop and think about it, there are vast numbers of different sources of stream data. An order book in a financial market is a series of time-stamped pieces of information, typically quite complicated. They're not necessarily all the same thing. I want to sell some IBM, I want to buy some Microsoft. A piece of ordinary text is a stream of data when you think about it. It comes in an order. The order matters. Change the order, you change the meaning. A hospital record or your health records are also a stream of data where the order of things matters quite a lot. Astronomical data is also that, where the order matters critically, but that's a huge data set, unlike the other ones. But it's a very noisy data set, so the problems are somewhat different. But the time in which things arrive is absolutely critical, and that's the whole idea of different telescopes in different parts of the world, is to get this data arriving at slightly different times. Perhaps a surprise for you, though, and that will come into at least one of the talks today, is actually our emotions evolving over time, if you record them in different ways, are also a stream of data where you can do useful and interesting things. So there's a very rich range that goes well beyond semi-martingales of different types of stream data. And what rough path theory did essentially was develop a unified way of talking about the analysis and algebra of these things. But I don't want to get involved in that technical detail too much. I want to get across one of the main reasons why this stuff has potential to be practical. On this screen, you'll see something we're all very familiar with, some rather badly drawn tree. And you've probably not thought about it, but we don't really care how quickly people move their hand round when they drew the tree. And indeed, different people may well do it in different ways, and an individual might from time to time do it differently. Certainly if I do it with the mouse, I do it fundamentally differently to if I do it with the pen. There is something here about this unparameterized image that's quite intrinsic and isn't preserved by the parameterization. So if we present that path in the way that would normally be done if you used Kolmogorov's approach, you would actually present its value at certain times. And so in fact you would have a graph. I don't know if we can make this point. You would have a graph, and here is time maybe, or maybe pixels. There are lots of different timescales you could use. And what's interesting here is actually these are both the same three, exactly the same three, but simply where, and this is the x coordinates of it, which if you think starts over with a small value and finishes with a small value, but a bit bigger small value because the 3 was sort of over one side. So this is the x coordinate drawn of that 3. And what you notice is that simply reparameterizing it dramatically changes what it looks like. If we look at both together, so this is the x and y coordinate. I challenge you, and the solid line is one parameterization, the dotted line is the other one. I challenge you to realize that's a 3. Right? But actually, this is what we normally do if we do machine processing of these things, because we think of it as a series of values at times, and we feed that vector into our system, a two-dimensional vector on this particular case, and we hope to recognize the patterns. But we're actually making life very difficult for ourselves because there's an invariance of the meaning under the symmetry of reparameterization, which is not reflected in the way we record the data. And so actually we have a large amount of actually quite irrelevant data, and we also get into stresses about things like missing data, which is really about simply which points we chose to take, and the fact that for some reason people feel they have to take the same points for each data set, each example. And that actually in the health context is really, really important, because a lot of real world data comes at different times and different amounts of measurements for different people. And we'll see that to some extent one has a tool here that will describe the 3 without describing the parameterization. So basically this is in a nutshell the most, or one of the two really significant reasons for what rough path theory does when it's describing real-world data streams. It knows how to describe them without introducing a parameterization. The parameterization isn't necessarily time, because you can take the path and time as the variable. The parameterization is more like when you sampled it. And if you sample it at different points, you do not actually change, if you have enough of them, the nature of the path, but you dramatically change the vector you introduce if you're doing a standard sort of machine learning. And so the reality is that we know how to do this. Now, one way to get out of doing it, what may have come to you, is, well, why don't we just parameterize the path at unit speed? But actually, this is nothing like as nice an thing as you might think. Here you see, this is actually a standard piece of commercial software, not academic software, it's free actually, I think, but that converts video images into skeletons of people. So it's mapping each person into something like maybe a 40 or 50 dimensional path. And the different bits of these people map at different speeds. Are you going to get it right for the feet? Are you going to get it right for the hands? Are you going to get the blinks of the eye right? The truth is there isn't a natural norm for measuring distances in high-dimensional situations. And moreover, in high-dimensional situations, more than one thing is happening at once. So the norm that would be right for one would misalign the other. And the truth is that any attempt to fix a parameterization and get out of it this way collapses once you're in high dimensions, or even lowish dimensions. But also this makes the point that actually the range of complicated objects that we can look at and try and understand is actually really quite rich. So how do we do it? So now for a little while I'm going to skip the soft talk, and I'm going to talk a little bit of mathematics for the people that are in the audience, mathematicians. I hope you won't switch off if you're not, but I will try and do it in ways that sort of make sense to everybody. So the big difference between rough path theory and classical ways of understanding paths was this appreciation that what you see isn't necessarily what you feel. It can be the case that you can have fine structure in your stream that includes lots of oscillations that have big enough consequences that you can't ignore them, even though you can't really measure them conveniently by sampling. And we've learned how to discuss that. And the way we've understood it is that you stop trying to say where something is at a time. It's really not what you do. Instead, what you do is you need a way of describing what something does over intervals. So the first thing you do is you throw away this sort of, I hesitate to say statistician, but this perspective that says, I just want to know the parameters. I just want to fit my model. Instead, you say, this is a stream of data, and I want to understand it in terms of its effects on other systems. And I can't describe what happens on every system. Well, I don't think I can. But I can look at what happens in very primitive nonlinear systems. I can look at the interaction. In fact, that's what these differential equations is. It's a sort of generating function. It's the non-commutative exponential. It's a generating function for some very simple nonlinear systems. And what we do is we say, well, actually, we're not going to say the value. We're going to say the effect on certain primitive nonlinear systems. And we substitute for the value this description. And this description is actually an element of a group. It's not commutative. It's quite simple or complicated depending on where you come from. And we entirely understand that this description over lots of little intervals is an effective way of describing what's going on. In fact, that was Newton's idea, really, with ordinary calculus. His view was that if I have a path, I can understand it quite well by looking at the chords. And that's an abelian summary over little increments, but it's much more complicated if there's a lot of oscillations and things, but it's not so different. So, right, and I promised that I would do a little bit of maths, right? So, the signature is this object that we look at. So we take our data and we transform it. We don't transform it into wavelets, which won't work because they're linear in the path and they won't see what's going on. We transform it in terms of its effect on systems, and we capture those effects and we call that the signature. And the signature is like any of these things. It transforms what you have into a series of numbers. It just so happens that these numbers don't depend on how you parameterize things. You can understand that because you're looking at the effect on the system over a period of time. And a differential equation like this, if we make gamma run faster, we just make S run faster. So when we reparameterize everything, we get the same answers if we fix the beginning and the end points. So it really is a function on path segments that ignores the speed at which you go along it, and it gives you a fixed set of features that really do quite a good job, even if you have more data sampling and less data sampling and so on. From a mathematician's point of view, you can interpret them, at least when the underlying stream is smooth, as integrals, iterated integrals where you do lots and lots, and you can understand these sequences of variables as giving you a top-down description. The first one tells you the biggest stuff. The next one tells you the slightly more complicated stuff, and in fact, the key point there is something called the area. The first one is the chord, the second one is the area between the path and the chord, and so on. And it's a math theorem that sequence of coefficients really does describe, in a very precise mathematical sense, the unparameterized stream. So it's obvious that given the stream you can get the coefficients. What is less obvious is given the coefficients you can identify the stream. But it's a transformation, and it doesn't actually waste much. That's why it works. It kills dimension quite dramatically. In practice, you don't need to understand this picture at all, but you don't look at the whole thing in general. You look at, because you're doing calculations, you look at numbers, so you look at elements in the dual space, and you let them project your complicated object down onto actual numbers. And so for each element of this dual space, you sort of get a sensor that will take your signal and produce a number. And this gives you, I want to do this because I want to explain that there's actually math in here. Because actually, when you multiply two of these sensors together, so there's the path, there's the sensor, and there's the path, and there's the sensor, then actually there's a purely algebraic expression called the shuffle product that tells you how you put those together. If you integrate one against another, there's another purely algebraic structure that tells you how to put them together. I'm not going to go into any of that detail, but it's actually very important, because one thing it tells you is that actually the space of linear functionals on signatures forms, thought of as sensors on paths, as measuring paths, actually form an algebra. We already know they separate points from the paper of myself and Hambley. So actually you see that they're rich enough to approximate any continuous function. So this gives them a universality. It means that any function can be thought of, at least locally, as linearly approximated by combinations of these. And linear things, you can use regression. You can actually really go and find those coefficients, and that's actually what one does. But I wanted to emphasize that this topic brings together a whole load of different areas. It brings together the analysis, which is critical to approximation. It brings the geometry of iterated integrals and Chen from the 1950s. It brings algebra, quite modern algebra really, in to understand the combinal structures. I mean, I have a working seminar at the moment in Oxford, and we're actually very interested in doing actual real computations, and we spend half our time reading really rather abstract algebra about how you manipulate trees and things like that, in order to understand better how to do things in practice. So this actually is a simple piece of software which I don't really have time to play with, but it's in fact computing not the signature but the log signature, because there's math that tells you to go between the two, and the log signature is a concise statement with no ambiguity. There's a one-to-one correspondence and no redundancy. The signature I told you about before has redundancy, but it has this wonderful property that every polynomial can be identified as a linear functional, so you can do regression. Mapping between those two is interesting. But anyway, the point I want to get here is here are two threes, and you see that roughly speaking, they have similar signatures, which is a good thing. If you look, small number, bigger number, the first one is the first two are the increments from the beginning to the end. The second one is, the next one, the 1, 2, is actually the area between the 1 and 2 coordinate. And then you get third order objects and fourth order objects and fifth order objects. If you look at the signs and magnitudes, they're broadly the same. And this is because we are measuring that path without the parameterization. It's completely stable, and it doesn't matter how you wrote it, you're going to get broadly the same. And in fact, one of my students who's not here, and now works in JP Morgan, actually has developed techniques that really practically go the other way. So you could go from the signature and draw a path that looked like a 3, just from these coefficients. And there are vastly fewer than you would need if you have wavelets. Vastly fewer. Because the wavelet's not even stable. You get things in different places and you need myriads of them in order to figure out the real relationships over all possible choices. And just to make that point, you see, you may not be able to see it, but the log signature's there, but the two Fourier series for these paths, these are the Fourier series for the x-coordinate, I think, are really very different. The coefficients are all over the place. They don't tell you what's going on, fairly obviously, really. In fact, if you think about it, reparameterization completely destroys even things like L2 norm, anything, and it's certainly not a linear subspace, right? If you take the collection of parameterizations of a path, you add two reparameterizations, you don't get a reparameterization. It's a very, very nonlinear concept. And you can easily prove, actually, that the approximation process that you would get if you use wavelets, if you use sampling, is doomed to be less successful than the signatures. And the way you can prove it is because Martin Clark, who's at Imperial and who's celebrating his 80th birthday tomorrow, and his student Cameron proved a very important theorem in probability and stochastic analysis many years ago, which asked the question, how well can you approximate the solution to a numerical SDE if all you know about the driving noise is its value at n equally spaced points? And he proved that in general it's never better than 1 over root n. And Andy Dickinson strengthened that later to say any n-dimensional linear summary has the same failing. So you see, wavelets are an n-dimensional linear summary. And so any way of looking at this path that is not intrinsically nonlinear will not be able to cope with the intrinsic nonlinearity of reparameterization. If you go with signatures and you take any linear differential equation and you have a p-rough path, then actually you can easily establish, or at least it's a serious theorem, that the convergence rate is actually like 1 over n factorial, which beats any geometric explosion in the coefficients. And so you know that you can do really strong approximation at a level which would be utterly, utterly inconceivable using the simple sampling. All of this allows you to tackle more interesting problems, and that's what I hope you'll hear during the rest of the day. You see, it's sort of obvious that that matchstick man, that path in something like 15, 20 dimensions, contains enough information in it to explain that that person is running. It's sort of obvious if I did the other ones, but I'm not going to, that there'd be enough information to understand what they're doing. It's a serious mathematical challenge to understand how to look at this data without getting into a muddle because of the dimension, and how to extract out of it enough information to make sense of it. It's a serious challenge to look at the Chinese handwriting, and you'll hear about that for sure later on. It's a serious challenge in the mental health to understand how people differ in their type because of their moods, behaviour. I'm basically finished. I just want to leave the last slide to say what's going on later, but I want to emphasize two things. First of all, that this is a huge effort with lots of people. I'm extremely grateful for the way they all do things. I think it's really exciting. But the other thing I want to emphasize is that this is not a panacea or a magic element, in the sense that it can't be used on its own. We're not talking about this coming out and doing everything because everything is a linear functional. It's sort of true locally, but we're actually talking about creative and imaginative ways of connecting this with all the other cleverness of data science. There's an enormous amount of clever ideas coming out that space, and we're talking about trying to make this a component that is valuable and useful in that context. So, for example, making it fit into pipelines so that you can use it in the standard pipelines of machine learning and things is the main ambition, really. It can be used as a tool with all the others, but it's a tool which is absolutely underpinned by a mathematical perspective on what this sort of stream data really looks like and how to manage it, handle it, and so on. And it's a rich one. You know, you're talking about dendriform algebras on one hand, you're talking about Hall basis for the logarithm to do real computations, you're talking about quite subtle analysis coming from Young. It's a very rich picture with many different perspectives. I think because actually non-commuting, free, evolving systems is very much a central part of mathematics, although we don't normally think of it as one piece. But it's also very, very much a part of our real world that we live in. It's not like images, which are sort of commutative. You go around that way, you go around that way, you get the same answer. Okay, that's all I wanted to say. Thank you very much for coming, and I hope you find it interesting.
We've got time for a couple of questions, comments.
Hi.
Hi.
You'll have to shout, Terry.
Okay. You didn't mention, or maybe in the first 2 minutes, that tree-like pieces of the stream of data can be regarded as irrelevant, or should be. I mean,
Sorry, I couldn't hear you. Did you hear?
It's not finished.
yeah. Well,
Speak up, please.
if you're trying to recognize handwriting and someone does this, draws a tree-like path, how do you recognize? I mean, the signature could interpret it as a trivial thing, but it is not.
Signature?
The signature of this is 1, but it is a minus or a.
Oh, that's a different story, right? I mean, and Leanne Wen could surely talk about it later on. I mean, that's what I'm trying to say. In fact, the way that you use the signature in understanding these images is not global, it's local.
Oh, yes.
And the way you understand it even locally is like Google Maps. Google Maps is something you can use locally to find your way around and to recognize where you are, but actually gives you no information that you could not deduce yourself by working. I mean, you could go out and walk and you can make your own map. There's no information in Google Maps. It's algorithmic benefit because it's pre-computed for you. The signature, in a way, does exactly the same thing. It allows to present the key information efficiently and quickly to make the next layer work well. And for those of you who want to think about the maths a bit, reparameterization is actually understanding paths on the line in a gauge invariant way. So the real numbers, I mean, if you think of that line as being unparameterized, it's just a manifold. Every parameterization is actually choosing a gauge in this one-dimensional context. And actually what you're trying to do is write down these paths in a way that's actually invariant under gauge transformations, and that's exactly what the signature does, in fact. Yeah.
I think we need to press on with the program.
Yeah, we'll sit down. That's great.
Thank you.